Okay, see this diagram here. We're going to have 3 of these diagrams on this page to get a sense of this new geometric shape. So we have a function. On top is f of x, on bottom is g of x. And I'm going to draw a rectangle that makes sense, a vertical rectangle that makes sense. The top is always the blue and the bottom is always the yellow. Now if I rotate this region R around the x-axis, again it's like summing infinite sum of these rectangles revolved. So let's get a sense of what that rectangle looks like if it is revolved around the x-axis. So what I'm going to do is come down here, symmetric about the x-axis, and I'm going to give you a cross section of what that revolution looks like. So like this, and this comes down like that. Can you see that shape okay? How would you describe that shape? Hopefully you're thinking or visualizing at least a washer. Here's a little art lesson to draw the washer. We draw an oval, horrible oval, but we come down here with some thickness and then I close it off. So that's a disc, but inside the disc I'm going to take away a disc. So I'm going to draw an oval inside, and if I draw this little loop there, it gives us some 3-dimensional feeling. And so the washer can go like this, or the washer can go in a vertical orientation such as we've drawn below. So let's discuss for a minute what the volume of this washer is. That's the key to it, so that we can infinitely sum a bunch of washers with an incrementally small or infinitesimally small thickness. So let's take a look at this formula. So the volume then is basically we have a bigger disk and we're taking away a little disk. So the bigger disk has the volume of pi, and then the bigger radius, or we might say the outer radius, and we're squaring the outer radius, and then we have a thickness. That would be the bigger disk. And then what we're going to do is take away the smaller disk, which has the formula pi, and then some inner radius, and we're going to square that times its thickness. We can also think of this if we pull out the pi and then also over here factor out the thickness, then we see the important features is going to be the outer radius squared minus the inner radius squared. That gives us the volume of a washer. So in this first example, again, we're going to talk about rotating about the x-axis. Alright, and then we're going to set up the integral to find the volume of the resulting solid. So the volume equals the integral, and we're going to start from a to b, and then it's pi that's got factored out of now the outer radius, and I find this to be really helpful. I'll use a different color here. The outer radius is going to be from the function to the axis of revolution. See, we're revolving around the x-axis, so this helps me to clearly see that the outer radius is this function f of x, and we have to square the outer radius. And then the inner radius, I'll use this pink color, so this inner radius is the distance from g to the axis, which is clearly going to be g of x squared. So now we have g of x squared. Close it off, and then the thickness of this rectangle, and hence the corresponding washer, the thickness is going to be dx. And here's just a fancier illustration of the washers that we could sum up to equal the volume. In the second diagram, we're going to take the same region R and we're going to rotate or revolve about some horizontal line y equals k, but we'll make k always bigger than f of x. So that axis of revolution will be somewhere like up here, and we're going to revolve around it. So let's take a look at our rectangle. A rectangle again, same rectangle. but this time we're rotating the rectangle up. And so if I draw that, we get a similar feeling. We have our washer, cross section of a washer is shown here, and we're ready to set it up. Our volume equals, this time I'm going to pull the pi out of the integral, and we're summing up from A to B. The outer radius now, let me put a bracket here, and then I'll start my outer radius. I'm telling you that you're going to find this real helpful. The outer radius is different now, and a lot of people at this point say the outer radius is g of x, but that's not exactly right. It's related to g of x, this outer radius, but it's not g of x. So the outer radius is going to go from here to the function g of x, and that is not g of x. This distance here that I've dotted, now that's g of x. So my outer radius, if I see carefully, is going to be the top of this distance minus the bottom of this distance, or k minus g of x. That will be my outer radius. Now, of course, I have to square my outer radius. Then I have to subtract some inner radius, quantity squared, and then I have my thickness. So the inner radius now, let me try to pick a different color. Let's go orange for the inner radius, and that's going to go from here to here, that outer radius being k minus f of x. Again, that's squared. Outer radius squared minus inner radius squared. Pi r squared thickness minus pi r squared thickness. Another fancy look at the solid, giving you a sense of what it would look like revolved around y equals k. In our last diagram on the first page, we're going to rotate or revolve about another horizontal line. This time, let's call it y equals c, where c is going to be less than g of x. So I could draw that here, I could draw that here, here. I'm going to go ahead and draw that down here. Y equals c, and we're going to rotate the region R about it. So we have a rectangle. We revolve. Now it's going to have a giant hole. So I'm looking at this distance here. Try to equal that distance. That's a big disc taken out of it. Oh, that's kind of ugly, but you get the idea of the cross section of the skinny thickness washer. Okay, let's set up to find this particular volume. So our volume now is going to be, pull out the pi times the integral from A to B. Now we're going to look at outer radius. So my outer radius, I'll get a good color here, white. Our outer radius is going to be the distance from here all the way down to the axis of revolution. So that radius is going to be f of x minus c, and I'm going to square that quantity. And then we're going to take away the inner radius, which is from this yellow g of x down to the axis of revolution. So that's going to be g of x minus c, quantity squared. Let's close this off, times the thickness of each, which is dx. Suppose that c is -2. The reason we're going to subtract, we would have the g of x quantity, and then we have minus a -2, so that would add 2 units to our radius. Fancy picture number 3. Let's take a look at examples 3 through 5. We have here a parabola and a line. I don't necessarily like the way those are written, so we're going to change them into a y equals f of x form. So we'll say y equals x squared plus 2, and over here in yellow we'll have y equals x over 2 plus 1, so that we have their functional values. So let's come over now to our picture, and I want you to see here that before we talk about revolution, this particular object, we don't have a lot of choices. In fact, we don't have any choice in the way that we draw our rectangle. Our rectangle has to be vertical. Skinny little rectangle has to be vertical. You see, if we tried to draw the rectangle this way, horizontally, well, the right of it is yellow and the left of it's blue. That's fine. But somewhere over here, it changes. And so we would have a region here, let's say brown. Then we'd have a separate region here of green, and then yet another region here red. So we would need 3 separate integrals if we were taking those rectangles and revolving them. So we want to stick with most efficient being these vertical rectangles where the top is always blue and the bottom is always yellow. And that's determined even before we try to revolve it. Okay, let's get some momentum here. So the first one here has us revolve this shaded region, gray, we'll call the region R, around the x-axis. Let's set up the volume. So our volume equals, pull out the pi, times the integral from 0 to 1. My outer radius, if I'm going to draw that, my outer radius is from the blue curve to the x-axis. So I have x squared plus 2 is my outer radius, and the parabola. And then the inner radius is going to be from the yellow line to white. And that's just x over 2 plus 1, quantity squared. The thickness of the rectangle, thickness of the washer, dx. Let's take a look at example 4. Same rectangle, but example 4 now has us revolve around the line y equals 3. So let's draw that y equals 3 here. You can see that we'll be rotating up. We'll set up the volume now. So the volume equals, pull out the pi, times the integral from 0 to 1. I've drawn here the distance from the axis of revolution down to the line. That's my outer radius. That will be represented by, that line is y equals 3, so it's 3 minus the line, x over 2 plus 1. I'll need this parenthesis because the negative gets distributed. That quantity gets squared, and then I'm going to take away the inner radius, and my inner radius is going to be this distance here, which is the line of 3 minus the parabola. X squared plus 2 is the parabola. That entire radius gets squared. We close it off with the thickness dx. Example 5 has us revolve the gray shaded region around the line y equals -5. Let's set up the volume here. Volume equals, pull out the pi, times the integral from 0 to 1. The outer radius is going to be from the parabola to our curve. So parabola minus a -5. So x squared plus 2 minus a negative gives us plus 5 for our outer radius, minus the line minus axis of revolution, which is x over 2 plus 1 minus negative plus 5, that is, quantity squared, thickness dx. In effort to make this video a little shorter, I would like you please on the next page to do only examples 7, 9, and 10 in that order. But I'd like you to force yourself to use a washer to find the solid of revolution. You may want to try each one by pressing pause and then unpause to reveal the solution. In example 7, we want to revolve around the line y equals 10. I will draw my rectangle vertically, and I will also rotate vertically, but I'll be rotating it up. And so my volume of the resulting solid will be pi times the integral from, this case, 0 to 4, my outer radius, 10 minus x cubed over 8, radius squared, minus the inner radius of 10 minus 2x quantity squared, thickness dx. Try example 9. In example 9, we're asked to revolve around the y-axis, but I've asked you to use a washer, so what we need here is to draw our rectangles in a horizontal orientation. See, so that rectangle will come over here, and that creates our washer shape. What gets interesting now, though, is that the radius is going to be the distance from here out to here. At least the outer radius is going to be from here out to here. That means we've got to translate each one of these into a function of y because they are currently functions of x. So this one is going to read x equals y over 2, while the next one, the cubic, will be x equals the cubed root of 8y, or 2 times y to the 1/3 power. We're going to need those functions. Let's set up to get the volume. So the volume is going to be pi times the integral from 0. Careful here, this is interesting. We're adding up rectangles, washers, starting here. The next one's here, next one's here. So in this case, we're going to go from y equals 0 to y equals 2 because we're going in the y direction. Our outer radius is going to be, already shown in that white line drawn, is going to be 2y to the 1/3 squared, and then our inner radius is going to be from axis to line, so that's simply going to be y over 2 squared. And then the thickness of every one of these rectangles, and hence washers, the thickness is going to be dy. Finally, example 10, we're going to rotate or revolve around x equals 25. Again, we're going to need a horizontal rectangle, and we're going to set up the volume, and our volume is going to be pi times the integral from 0 to 2. My outer radius this time is distance drawn like this, so 25 minus line, so 25 minus y over 2 as the outer radius, and the inner radius is going to be this distance here, and that's going to be 25 minus 2y to the 1/3 power. We're going to square that, thickness dy.